Our first problem involves the acceleration of the space shuttle at liftoff. The problem reads, the 3 space shuttle main engines and the 2 solid fuel booster rockets develop a total of 29.7 times 10 to the 6 newtons of thrust at liftoff. If the total mass at liftoff is 2 times 10 to the 6 kilograms, what is the acceleration at liftoff? Let's first of all watch the motion of that rocket. Here is our rocket on the launching pad waiting for liftoff. The rockets come on and the space shuttle accelerates upwards. The problem is to determine the acceleration of the ship at the moment of liftoff, that is, at the moment when the rocket just leaves the ground. Alright, that's the problem. Why don't you stop your VCR at this point and attempt to solve that problem before you watch the solution. We'll solve our problem on our computer-generated blackboard. I have listed the information given in the problem, that the thrust is 29.7 million newtons, the total mass is 2 million kilograms, that the magnitude of the acceleration of gravity is 9.8 meters per second per second. The direction of the acceleration of gravity is, of course, downwards. We will indicate this direction when we draw our vectors for weight. I've also listed the Newton's second law, that the net force is equal to the sum of the forces acting upon the mass, using the common symbol for summation, that is equal to the total mass multiplied by the acceleration. The first thing to do in solving a problem like this is to draw a free body diagram to isolate the mass in question, here a space shuttle, and draw all of the forces acting upon the mass. One of the forces acting upon this mass and on all masses is the weight, which acts directly downwards or towards the center of the Earth and has a magnitude mg. Also, we have the thrust, which acts directly upwards on the rocket. We'll draw a vector upwards and call that T for thrust. These two forces are the only forces acting upon the shuttle. If we ignore friction, and we are ignoring friction in this problem and in all our problems unless it is explicitly stated. They are all the forces acting upon the mass, so we can write Newton's second law then as T, using upwards to be positive, that's plus T, downwards direction being negative, so minus mg is equal to the mass times the acceleration. The acceleration, if we solve for that, that is what we want, is then equal to T minus mg divided by the total mass m. And if we plug in some values for our quantities, we have then that A is equal to T, which is 29.7 times 10 to the 6th newtons, minus m, 2 times 10 to the 6th kilograms, times the magnitude of the acceleration of gravity, 9.8 meters per second per second. We divide all this by the mass, which is 2 times 10 to the 6th kilograms. If you use your calculator to evaluate the numerator, you will find that that comes out to be 10.1 times 10 to the 6th newtons. We divide that by 2 times 10 to the 6th kilograms. That works out to be 5.05 meters per second per second. So that's our acceleration. Round it to 3 significant figures. I'm going to assume that all our data are accurate to 3 significant figures. So that is our acceleration. It is not an excessively large value for an acceleration. It is less than the acceleration of gravity. It does change. That is the acceleration at liftoff. But as the rockets burn fuel, the mass of the rocket decreases and the acceleration of the rocket increases. The acceleration increases so that the maximum value for the acceleration that the astronauts experience is approximately 3g. All right, that is our solution. Let us move on now to our next problem.